Hello, everyone. Welcome to today's Cooped Up, our initial offering from Metrum Research Group. My name is Matthew Riggs, the Chief Science Officer here at Metrum. I just wanted to introduce the concept of Cooped Up to everyone. This is our acronym here is Cellar Office Open Education in Pharmacometrics. That's where the Cooped Up idea came from. And really the idea here is to introduce and open up the community to a lot of the training concepts that we do here internally at Metrum. We'll often meet on Mondays at noontime for these types of educational offerings, either going through a particular paper that's come out or a classic paper, manuscript that a scientific topic, or sometimes just training sessions going through some methodologies and such. And so the idea here is to begin to share those on occasion. Certainly at the demand and desire of the community here, we'll welcome feedback on this. Today, in the interest of time, I don't want to go too much more in depth with that. I'd like to introduce Tim Waterhouse, a principal scientist here at Metrum Research Group, who's going to give us an introduction to optimal design in pharmacometric models. Note that Kyle Barron is also joining us as one of the panelists. Kyle is the developer of the mrgsolve package. You'll see quite a bit of that sprinkled into Tim's presentation here today. And so Kyle will be available for some of the questions at the end as well. Tim will be doing the bulk of the presenting. We do welcome any questions that individuals may have. If you could add those into the chat window during the presentation, and then at the end we'll get through as many of those questions as we can in the time remaining. That said, Tim, if you could please take it away.
Okay, all right, thanks, Matt. So yeah, thank you, Matt, and thank you everyone for joining us to spend this next hour or so being cooped up with me here to talk about optimal design. I'm going to be talking about optimal design using a couple of pieces of software, PopED and mrgsolve. I wanted to include the PopED logo here because I'm making such heavy use of it, but I'm including a little fake legal disclaimer just to emphasize that this is not something that I or Metrum are involved with other than being happy customers. Okay, so why are we here? So primarily, I wanted to share with you some soothing pictures of nice, colorful rubber ducks to help distract you from the horrors going on in the world outside today. But while we're doing that, let's talk about optimal design. So I'm assuming that you want to design a study of some kind, and that when you have results, you'll be fitting some kind of pharmacometric model, and that you don't want that model to fail spectacularly. So to do that, you could use simulation. You could run a bunch of simulations to evaluate some designs and see if everything is going according to plan. But depending on the model and the design, this could be very time consuming. So to do that, we have some tools in optimal design to help you do that a lot more quickly and efficiently. So in this talk, I'll give you some background on the ideas involved with optimal design, some of the tools that we have available to us to use those ideas in practice. And to do that, I'm going to work through a few examples. I'm going to start with a simple PK model in PopED and show you how I can use that to evaluate some designs, optimize designs, and then outside of PopED, run some confirmatory simulations. And then after the simple example, I'm going to move on to some more complex PK models and PK/PD models with differential equations. And the process here is the same, but adding the differential equations makes this a lot more tricky in practice. So I'm going to show you how to integrate mrgsolve into that practice. So up the top, I wanted to acknowledge a few people who have helped put this work together. Kyle for helping with the mrgsolve models, Devin and Seth for helping me get started with the Babylon modeling platform, which has helped to run these simulations. Before I get into this, I wanted to start with some audience participation. So for the poll question here, I want to know what your current level of experience is with optimal design. Maybe you've never heard of it before this talk. Maybe you've seen it around a bit and you'd like to try it out. Or maybe you're a bit of a skeptic. You've seen it, but you don't really trust it. You think that this simple calculation is not really going to do anything good for you. And I do want to know if you feel that way. This poll, by the way, is anonymous, so don't hold back. Let me know if that's really your feeling. Maybe you have actually used optimal design before, and maybe you're a complete expert, in which case I don't really know why you're here, but I welcome you anyway. And maybe you're distracted right now and you're not listening to me, but that's fine. All right, so Joe, would you mind putting up that first poll question, please? Just take a little time to collect these results. Okay, all right, I think that's enough. I don't know how to show the results. Can I do that? Let me see, polling. Okay, let's see. So we're getting quite a lot of people for number 2. That means, well, that's, I think, kind of where I'm aiming this topic at, which is that you've seen it around and you want to try it out. We do have some skeptics in the audience. That's good. I hope to turn you around by the end of this talk. And quite a few people have actually used this before too. And we have one expert in the audience. That's fantastic. All right, so let's get moving. So let's start with some background on optimal design. So in optimal design, we have a whole bunch of criteria that we can use, but most of them revolve around this one thing. Not the thing on the right. This is a North American mammal called a fisher, which is apparently some kind of relative of the weasel. But we're talking about the thing on the left. This is the Fisher information matrix. This is a function of psi is our vector of population parameters, which are the thetas, omegas, and sigmas in your non-mem model. And it's also a function of this vector xi, which is your vector of design variables. And that means anything that you can control in your study. So it could be PK sampling times, it could be the number of subjects, the dose levels, covariates that represent your population, things like that. So why do you need to know about the information matrix? Mostly because of this result in statistics, the Cramer-Rao lower bound, which tells us that if you invert that information matrix, it gives you a lower bound of the covariance of any unbiased estimator of your parameters. Which means that if you look at the diagonals of that inverse, you can get lower bounds of your standard errors of the parameters. So with a quick matrix calculation, you can have a lower bound on your parameter precision. So this is really helpful. It gives you a really quick way to evaluate a design. Okay, but really, why do you care about it? Well, so like I mentioned, there's a bunch of criteria for optimal design. The most popular, the most common is the D-optimality criterion. The D here stands for determinant. So a D-optimal design will maximize the determinant of the information matrix. This is useful because maximizing that determinant, because of this relationship here, it's equivalent to minimizing the volume of the confidence ellipsoid of your parameter estimates. What does that mean? What's a confidence ellipsoid? Well, in a single dimension, it's just a confidence interval. So if you have a single parameter, you're minimizing the width of that confidence interval. So you're making that parameter estimate as precise as possible. If we extend this to 2 dimensions, say we have estimates of clearance and volume, the shaded region here shows you a confidence ellipse. So it's a 95% confidence region for these parameter estimates. So it could vary anywhere in that region, 95%, with 95% confidence. So a D-optimal design will minimize this area. So this is not necessarily going to be the best design in terms of clearance or the best design in terms of volume, or it's not going to necessarily treat them equally, but it's going to minimize the overall area here. If you are interested in particular parameters, say you only care about clearance, then there are other criteria that you can use instead of a D-optimal design. But there's a catch. This information matrix depends on your parameters and your design, but for a linear model, the dependence on these parameters disappears when you take the derivatives involved in that calculation. But unluckily for us, we're usually dealing with nonlinear models. So the information matrix depends on the parameters, which means in order to design our experiment such that we get the best estimates of our parameters, we need to know the values of those parameters before we design the study, which doesn't seem particularly helpful. But it gets worse. Not only are we dealing with nonlinear models, we're usually dealing with nonlinear mixed effects models, which means that we don't have closed form solutions for the likelihood, which we need to calculate the information matrix. So we rely on approximations. There's some references here which describe some of those approximations. So it means our information matrix is an approximation to a lower bound that depends on the parameter values. It doesn't sound great, but all is not lost, because usually we have adequate information on parameter estimates. Usually we have clinical prior experience, or we might even be extrapolating from animal data or somewhere else if it's never been studied in humans before. And these approximate lower bounds are actually usually good enough. In practice, when you run simulations to check the design, we find that they're not far off. That's not always the case, and there's more to that to come, more on that to come. So optimal design can be used to optimize designs, of course, but we can also just use this information matrix to quickly evaluate a design, to calculate the relative standard errors. A lot of the time, optimization is just a last resort, so we can evaluate a handful of designs and find that at least one of those is good enough to move forward. But sometimes there are situations where, for some reason, you're not able to find a good design just by using intuition, so you need to optimize using a search algorithm. So I'm going to show you some examples of that. Okay, if you do optimize a design, you'll often find that the sampling times that it gives you are not practical. So it could be that the sampling times are in the middle of the night. It could be lumping them all together. That's something that the optimal design often does, is give you, say, 2 or 3 samples all at the same time, which you are not going to take in practice. So you can tweak those by constructing sampling windows around those times. Even if you're not optimizing a design, you can't always collect samples at precise times. So if you put 2 hours in your protocol, what happens if you collect a sample 5 minutes or 10 minutes or 20 minutes before that time? So you can construct windows around these times even if you're not optimizing. And there are ways of optimizing the width and the placement of those sampling windows, or you can just determine them manually and look at the effect on the design. So there's a number of tools available for optimal design in PKPD. This table is from a paper a few years back comparing 5 different software packages that did this. As far as I can tell from a quick Google search, all you'll find on the web today are PopED and PFIM. If that's not the case, if you know of others that are online right now, please tell me. But today I'm going to focus on PopED, which has been around for quite a while. This was originally developed in Omatrix and MATLAB, and it's been ported more recently to an R package. There's a link here to the package website. We'll be sharing these slides and the related code later on, by the way. But I would highly recommend you also check out this website. If you're interested in using PopED, there's some great documentation there. It's very helpful to get you started. So after we optimize or evaluate designs, it's important to use simulation to check. The concept here is not particularly complicated. All we're doing is taking our design and replicating a large number of studies. So in this example, I have 100 different studies. So I take, say, a non-mem control stream, a template for that, and then I use an R script to generate replicates of those studies, run them through non-mem using this modeling platform called Babylon, which has, there's an R package associated with that, which acts as an interface between R and Babylon. So all of this is run through one script. So we can create our template datasets and control streams, run the non-mem models, and then also use RBabylon to collect the results together and summarize the distributions. So there are tools available out there to do that, things like SSE in PSN, but I'm just doing this all in one R script since I'm doing my PopED in there as well. So let's get to our first example. This is a simple PK model where we have a closed form solution. So suppose we have a drug, moxidrosine. We've studied this drug in adults, and we want to design a pediatric study. So we want to evaluate PK in the pediatric population, but because they're kids, PK sampling is going to be pretty sparse. So what we want to do is make sure that these sparse samples are enough and timed appropriately so that we can get good PK parameter estimates. It's going to be a small study, only 12 subjects, age 6 to 12. We're going to dose them for a long time, 10 milligrams daily for 24 weeks. And we have a very sparse proposed sampling scheme. So a single sample on day 1 at 5 hours, some trough samples throughout the study, and then final dose 1 week after the last dose. So the question is this sufficient to get good parameter estimates? And this is the model that we're trying to estimate the parameters for. It's a simple one compartment model with first order absorption. So we have parameters for clearance volume and Ka that we have estimates for from adults, and we're going to use fixed exponents of weight on body weight on clearance and volume. And we have variability, inter-individual variability on these parameters, as well as a combined additive and proportional residual error model. And this is a plot of the typical profiles. You can see it has a very short half-life. We reach steady state very quickly. So when we use this model in PopED, any samples past the first day, I'm just going to assume are at steady state, which makes the computation a bit simpler. Okay, let's do a bit more audience participation. So now I want to ask you what you think will be the best design. So not for that particular situation, we're going to use that same model now just for a single dose in adults. The plot here shows you the typical profile, and I want you to choose one of these 4 design options. We're going to fix the last 3 samples in the terminal phase here, 24, 48, and 96. What I want you to do is choose where that first sample should go to get the best estimate of Ka, the absorption rate, keeping in mind that our Tmax is going to be at around 6 hours. So the first option is to put your sample here at 1 hour. The second option is to put it at 4 hours, or do you want to put it at 6 hours or 12 hours? Or maybe you're not listening to me at the moment, and that's fine too. Okay, so Joe, can you pop up that next poll question, please? Okay, I think that's enough time. So let's see what we picked. Okay. Oh, this is a fairly even distribution. Okay, so we're seeing the most popular was still only 44%. First sample goes at 1 hour. Next most popular was 4 hours, then 6 hours. Nobody said 12 hours, which I'm kind of relieved about. And someone's not paying attention, that's fine. Okay, let's see what the answer is. So if we run this through PopED, these are our expected relative standard errors. So the answer is you want this sample to be as early as possible. So that would be here at 1 hour. It turns out, as the further you get away from that optimal sample, the higher your standard error, but there's really not a whole lot of difference. So even though you might not have chosen the actual optimal time point here, you wouldn't have gone too far wrong. And of course, nobody chose this one, in which case your standard error would be probably higher than you would want. So in cases like this, your intuition probably does a good enough job, but I hope I show you with some later examples that you really do need something like optimal design to choose your design well. So let's get into the PopED. So to set this up, we need to define our model. And to do that, we need to set up 3 different functions. One to define your structural model. So that would be your equation, basically your advan type equations. Then your parameter model, which describes how the inter-individual and inter-occasion variability, if you have any, work. And then there's a residual error model. So these 3 functions together will define really what you set up in the same type of thing that you set up in your non-mem control stream. And then we bring them all together with this function called create PopED database. So it collects together these 3 model functions. We specify the values of the parameters and everything else related to study design. So this could be sampling times, doses, the number of subjects, as well as anything that defines your design space, which means what you're going to search over in an optimal design. So the boundaries on your sampling times, for example. Once we've set this up, we can check using this function plot model prediction, which shows you a typical, I mean, you can include variability here if you like, but this is just showing a typical response as well as the sampling times in the initial design. So the 2 plots here show that I've set this model up using 2 separate models. There's a single dose model for our day 1 sample, and then a steady state model for the trough samples here, and that final sample 1 week past the last dose. Okay, so once we have this set up in this database object here, we can evaluate the information matrix using this function. For a simple model and design like this is pretty much instantaneous. I'm not going to show you what this matrix looks like because it's not particularly helpful, but I will show you the determinant of that matrix is this number here. Again, the value of this number is not particularly useful, but when it comes to optimizing designs, this is the value that's going to be maximized. What's more useful are the relative standard errors based on the information matrix, and that can be done just using this function, get RSE. And this is the output that you'll see from this function. I didn't show you all of the nitty-gritty of setting up this PopED database, but the BPOPs here are the fixed effect parameters, so the thetas in your non-mem model. The Ds are your omegas, and the sigmas are your residual error variances. And the numbers here are your % relative standard errors, which are clearly enormously high here. So we have some numbers here in the millions. So there's some kind of numerical issue happening here. My guess is that we don't have enough support points in this model, sorry, in this design, which would be, where are we? Where's our design? So we have 1, 2, really, let me go back to the plot here. We have 3 distinct sampling times, so 3 support points. So we're going to need more than that to estimate all of these parameters. And so I do that here by modifying this database object here by specifying a new set of initial sampling times. These are all the same except for 1 point. So I still have the 5-hour on day 1, 3 almost trough samples, and then that 1 week sample. I'm just bumping this 1 trough sample down to 23 hours instead of 24 hours past the dose. And you can see that this has brought our expected relative, whoops, excuse me, let me draw a box around that instead. That has brought our expected standard errors back into reality, but they're still very high. So we need to do something about that. Okay, so let's use a de-optimal design to try and optimize these time points. So when I set up this database, I specified the initial sampling times, but I also specified bounds on those. So using min-xt and max-xt that sets the lower and upper bounds. So the first sample is 5 hours in our initial design, but when we optimize it, we let it vary between 0 to 6 hours. Our trough samples at 24 hours will allow that to be anywhere up to 1 hour before that pre-dose sample. And our final sample 1 week after the last dose can be anywhere from 4 to 7 days. So we optimize it using this function. We specify that we're optimizing sampling times rather than some other variable. And let's look at the output. So very quickly, so you can see this took less than 10 seconds, we've optimized our design. Model 1 here shows you the single dose sampling time. So this is the day 1 sample, has moved back to about 20 minutes after the dose. Our trough samples are mostly untouched, except one of them has moved back to 23 hours before, just as we did in the previous example. And our final sample has moved back to 96 hours. So this is kind of one of the artifacts of de-optimal design. It tends to push your design points towards the boundaries. So we started up at the upper boundary, and the optimal design has pushed it down to the lower end of that boundary, 96 hours. Okay, what's useful here are the expected relative standard errors. These are percentages. And this shows you the RSEs for the initial design. So this is what we were looking at before with these RSEs in the millions. And these are the RSEs for the optimized design. So for our theta variables, this is clearance, volume, and Ka. We're now in a more kind of reasonable space, but we're still way too high. So our volume and Ka both have RSEs above 100, to say nothing of the omega estimates. So we need to add another sample in here at some point. So let's try adding one extra post-dose sample at steady state. So we have this one post-dose sample here on day 1. Let's add another one at steady state. So I didn't show you the details before, but the first element here, whoopsie daisy, was it is defined in the model to come from the single dose PK model. Everything else is coming from the steady state model. So this 4 here is going to be 4 hours after the dose at steady state. We're going to allow that to vary between 0 and 6 again. If we evaluate that initial design, we're doing a little bit better, but not really good enough. The Ka is still 120, 120%. So let's optimize over this space. So we use the poped optim function again, and this is the optimized design. Again, this is very quick. In 13 seconds, we have an optimized design. The day 1 sample is now pushed up to the upper boundary, 6 hours. That post-dose sample at steady state is going to be at around 1 hour. Then we have our trough samples, and then that final sample at 96 hours again. This is doing much better now, at least in terms of your fixed effect. So your theta RSEs are much more reasonable, but our omega RSEs are still pretty high. 120% is probably higher than you would like. So let's try one more thing for this example. We're going to try adding instead another sample sometime after the final dose. So this doesn't have to be within 6 hours. This can be anywhere up to a week after that final dose. We're going to start with a sample at 72 hours and let that vary anywhere from 0 to 168. So this is, again, just evaluating. This is a pretty much instantaneous evaluation of that initial design. Doesn't really help much, so we need to optimize, and we can do that pretty quickly as well. And these are the results here. We have a sample about half an hour on day 1, roughly trough samples at 23 hours at steady state. And then these 2 samples after the final dose, around 41 hours and 168 hours. And let's look at the last column here. Everything's looking pretty good. The fixed effects are looking great. The omega estimates are a little high. 60, 70% is probably maybe higher than you need, than you'd want usually, but we're going to pretend that that's good enough for this study. Okay, except that the sampling times here are not really practical. We're not going to put 0.4454 hours in our protocol, so let's round that to half an hour. 1 hour before a dose, maybe asking a bit much, so let's just pretend that these are coming exactly at the pre-dose time. Because they're in the terminal phase, it's probably not going to change anything anyway. And this 41 hour sample, if we're dosing in the morning, this is going to be in the middle of the night, like 1 a.m. or something. So let's move this back to an afternoon sample. Again, this is in the terminal phase. We're not expecting this to change the estimates that much. So we're going to assume that we have a lot of leeway and see what happens. We'll leave that last sample at 1 week. So we set up the sampling times as I described, and let's evaluate that design. So our standard errors have crept up a little bit since this is no longer optimal, but we're probably in a reasonable area. This one here is the standard error for your volume of distribution omega estimate. A little high. If you do care about that, then you want to spend some more time optimizing. And this is just a plot of what the final design looks like. The early sample on day 1, your trough samples, and then these 2 samples past the last dose. Next thing we want to do is put some sampling windows around these. So we do this using this function in PopED called plot efficiency of windows. And what it does is this creates a number of replicates of your study, and it samples the sampling times, or generates random sampling times between some intervals that you specify. So I'm going to say that for each of our sampling times, I'm going to give an upper bound and a lower bound. So for that half-hour sample on day 1, I'm going to let that vary a quarter of an hour before and after that sampling time. For the trough samples, I'll let that be anywhere up to 1 hour before the dose. And I'm going to put 2 hours either side of that 32-hour sample and up to 4 hours before the final dose. And these plots here show you the effect on the expected standard errors for all of these replicates. So each point here represents a different replicate of a simulation of sampling times. So, and the y-axis here is the standard error for a particular parameter. So this square here is showing you the clearance. Oops. Is showing you the standard error of the clearance. Doesn't really change much. So between 9.75 and 10.5 is really the range that's changing in. So we don't really care about that at all. If we look at the other parameters, they're not really changing much either, which means that any deviation within these windows is going to be fine. But we do want to confirm this result with simulation because of the fact that it's an approximate lower bound. And so we run simulations with non-mem. So we generate, for this example, I did 100 replicates. I generated 100 control streams and then 100 data sets with sampling times randomly within those intervals. And the box plots here show you the distributions that we get from those 100 parameter estimates. So the blue ones are our thetas, the red ones are our omegas, and the green ones are the sigmas. And this is the first time that we're looking at bias for these parameters. So the information matrix, as far as I know, can't tell us anything about bias, but the simulations can. So this is showing us relative bias for each of these parameter estimates. So we can see that, maybe our clearance omega here is a little bit concerning. If this is an issue for you, then you might want to try to correct that in your design. Something else we want to look at are the actual standard errors that we get out to compare them to PopED. So the first column here is what we've already seen. These are the numbers calculated from the information matrix. The second column are the same standard errors from the simulation. So because this information matrix gives us a lower bound, we do expect these to be higher on average. And in fact, each one of these is at least a little bit higher than what we'd expect. Most of it is not really an issue though. The only ones that might give you some concern are the volume and Ka omega estimates. They're starting to creep up into something that are probably not really acceptable. So you might want to try to, again, go back and evaluate some different designs here. Okay. So let's ramp things up a bit by introducing differential equations. The process here is not really any different before. The only difference is that we need to solve differential equations every time that we evaluate our model. And this just takes time. So when I was a fresh-faced young PhD student doing optimal design for the first time, I did some designs for differential equation models, and it would take 2 weeks to run an optimal design. This was in MATLAB. I did some in S+. We didn't have the tools that we have now to create compiled differential equation models easily. I might have been able to do that if I had some more know-how, but now we have mrgsolve, we have rxode. There are some other options. If you look at the PopED website, it goes through some nice examples there. I'm going to show you how we do this with mrgsolve much more quickly. Okay, so in this example, we're going to look at an antibody, faecunumab. It's going to be studied in humans for the first time. So we're going to run a large range of doses, single doses with 6 subjects per dose group. And we have a proposed sampling scheme with 7 different sampling times, up to 3 weeks after the dose. And from animal data, we're expecting a 2-compartment PK model with linear and nonlinear clearance. So these are our parameters and their estimates. We also have variability in some of these parameters and a proportional residual error. Okay, so instead of just writing a simple R function to specify the model as we did for the previous example, I'm going to use mrgsolve. So mrgsolve is an R package which does simulations from differential equation models. And it does it much quickly than you can do from, say, the built-in differential equation solver in R, because it compiles the model. So to set up this model, we specify the parameters and the default values. Just like in non-mem, we declare the compartments. We do some rate constant calculations, and then set up the differential equations themselves. So there's not much to this model. And then we output the plasma concentrations here. So in a typical mrgsolve model, you would also include variability. You'd have your etas and epsilons, just as you do in non-mem. But for this, for PopED, PopED is going to handle that part of it. We'll have separate functions, the FG functions and the residual error model functions that handle those parts of this. So this is the FF part of the model. FF, it's a convention, naming convention, I think, to specify the structural model. So we're going to set up a dosing object, an observation object, and feed them into this mrgsim function, which does the actual simulation. So this is the function from mrgsolve. And just to check that we've set everything up right, we plot the responses for the 6 dose groups and the initial sampling times over 3 weeks. And everything looks good. So we can evaluate the information matrix and look at the standard errors. And in fact, these all look pretty good because I spent a lot of time with this example before setting this up so it will work nicely. All these residual relative standard errors are good for our thetas and omegas and sigmas. So I'd be happy to run this design. Just as a note, I did try to optimize a design using this model, setting this up, and it took about 45 minutes, which is a long time compared to 10 seconds for that closed form solution model. But compared to 2 weeks that it has taken in the past for me, this is a lot quicker for a similar model. And again, we can generate sampling windows using this same function, plot efficiency of windows. I'm going to say will allow, so the units are now in days. So this is saying 1 hour either side of the day 1 samples and 3 hours either side of the remaining samples. And we can see that the expected standard errors don't change considerably. One thing I didn't mention before was, can I do that? Nope. One thing I didn't mention before was this little plot here shows the efficiency of each replicate design. The efficiency, without going into the definition, it describes the proportion of information. So the proportion of more information that you get from a design compared to some reference. So the reference here is the initial design. And because that initial design in this case was not an optimal design, I just kind of chose it after playing with a few. it looks like in most cases here, any deviation from that by sampling within these windows is actually improving the efficiencies, which is a good thing. And again, I ran some confirmatory simulations. Again, this is the first time we're looking at bias. So there may be some slightly concerning bias around these omegas again, but overall it looks reasonable, I think. And we can compare the expected and simulated standard errors. Let's have a look at those again. So these are our expected standard errors from the information matrix. And these ones are from the simulations. So mostly they're in the same ballpark, at least. One of them is actually slightly lower. The simulated standard error is actually slightly lower than what we'd expect. But there's one fairly concerning thing here, and that's theta 3. This is Km. So we would expect from the information matrix to get an 8% standard error, but in practice with the simulation, this is much more variable. So if this is concerning, if you would want to estimate this more precisely, then it would be time to go and actually optimize this study. Okay, the last example I have is a PK/PD model. So until now, we've only been talking about optimizing PK sampling times, which is fine. It's actually probably what you're going to be using this most for. But optimal design can be used to evaluate or optimize any component of a design. So that means doses, number of subjects, any covariate values. So for this example, I'm going to show you how we can evaluate some dose levels in a PK/PD study. So this time, I'm going to be using a real drug and a real model. So this is from this paper on filgrastim. The non-mem model has been published on DD Moore. Kyle has translated this to mrgsolve, and this is available at the depot here. But so the doses, the drug is real, the model is real, but this study that I'm presenting here is fictional. I'm going to suppose we have daily doses, subcutaneous doses of filgrastim at initially these 3 dose levels, 1, 3, and 10 micrograms per kilogram. And in this study, we'll have 10 subjects per dose group. And I'm assuming that we have dense, very dense sampling for our PK and PD responses. Because the focus here, I just wanted to focus on the dose levels. So it is possible to simultaneously optimize for sampling times and for doses, but I'm just going to assume that we have more than we need, more samples than we need for these responses. So this is a diagram of the model. We have the PK model on the top, and this is a neutrophil model on the bottom, and they're linked through these indirect response models. So filgrastim will stimulate the neutrophil proliferation here, as well as the transit rate between these compartments. And they're described by these 3 distinct parameters. So there's an SC50 parameter, which is shared between all of these parts. And there are 2 different Smax parameters. There's an Smax for the Kn and another Smax for the transit rate, constant Kt. So we want to make sure that we pick the doses that give us the best estimates of those 3 parameters. These are what some typical responses look like for a range of doses. So from 0.1 up to 30 kilos, micrograms per kilo. We have PK on the left and the neutrophil, the PD response on the right. So our initial design, the proposed design is to put 3 doses, 1, which is the light blue here, 3, which is the green, and the 10 microgram per kilogram, the kind of brownish, yellowish color on the top here. Now, but we want to know, can we actually push those doses down a bit? Will that improve our model fit? I'm going to assume for this purpose that we have some kind of fictional toxicity above 10, so ignore the 30 micrograms per kilogram. Okay, but instead of optimizing this, I'm going to ask you what your opinion is. Okay, first, let's look at the initial design. There's a lot of parameters here. No need to look at all of them, but trust me, they all look pretty good. I want you to focus on these 3 here. So this is the theta values for this is your SC50. The standard error is 21%, and the two S max parameters are about 8% each. So these are all fine. You probably have no trouble running this study without, after first, of course, running some simulations to check that these are reasonable. But what I want to ask you is if you think you can improve on this. Let's see. How do I clear that? Okay. So the last poll question, I want to ask you, are there any better doses for estimating those parameters based on what you've seen here from these responses? Do you want to stick with the initial design of 1, 3, and 10? Do you want to move all of those doses down? So that's 0.3, 1, and 3 micrograms per kilo. Maybe you want to keep the top dose at 10 and just move the lower doses down, so you get a better range of doses here. Or maybe you want to move all the doses down and go all the way down to 0.1 micrograms per kilogram for that lowest dose. And maybe I'm on mute and you can't hear me right now. I hope you can. Okay, so Joe, could you please pop up that last question? Okay, so hopefully that's enough time for you to optimize that design in your head and pick some doses. Okay, let's take a look at those results. Here we go. All right. Wow, there is a consensus here. Oh, this is great. Okay, so number 3. So 0.3, 1, and 10. I think maybe I misled you a bit. Yes, you get a bigger range of doses here. You get from 0.3 all the way up to 10 micrograms per kilogram. It looks like most of you have chosen that. Some have chosen the other options. That's fine too. Let me show you the result. So the answer is actually most of these are pretty good. Whether you choose the optimal one or not is really not going to make much difference here. But it turns out that the best of these designs was the first one, 1, 3, and 10. So if you do push those doses all the way down, well, if you have the biggest range of doses here, you're actually going to increase your standard errors, but only by a slight amount. Really, any of these choices is going to give you a reasonable estimate of each of these parameters. I think that's just because of the fact that we're getting such a big range of responses even within the higher dose groups, that it doesn't really matter that we're not going down to that lower dose level. Okay, but hopefully, I'm glad that actually that a lot of people chose this one, just to show you that our intuition isn't always reliable for these kinds of designs. Okay, so let me wrap up quickly. So I hope you learned something out of this. I hope you've learned that optimal design can be a useful tool, even if it's not perfect. And because it is imperfect, I hope I've convinced you to always run confirmatory simulations. The output from an information matrix is approximate and it's a lower bound, so always check it before you run your study. And optimal design is not just for PK sampling. That may be what you use it for mostly, but don't forget that this can be used for any aspect of your design. There's a lot that I didn't cover today. So the first thing is, in these examples, I'm assuming that I have perfect knowledge of the parameters in the models, which is obviously never going to be the case. And there are optimality criteria that we can use to deal with that. We can also deal with uncertainty around the structure of the model. So we may not know for sure if we're using linear clearance or nonlinear clearance in our final model fit. Maybe we don't know for sure if it's 1 or 2 compartments, something like that. So there are criteria to deal with that as well. You can focus on particular parameters if you like. If you don't really care about every single parameter in that model, there are criteria to deal with that. And there's basically a whole alphabet of other optimality criteria that do different things. And I also haven't shown you pretty much all of the options in PopED. I would, again, advise you go and check out that webpage. There's some great documentation there. This is the link to the mrgsolve webpage, which has a wealth of resources as well. There's tutorials, videos, there's a user guide, blog posts. Check that out. And then I mentioned I'm using Babylon and RBabylon for the simulations here. So these are some web pages there. Some references for what I've shown you today. And I'd like to thank you for your time. And I'd be happy to take any questions.
Tim, thank you very much. So please feel free to type in some questions. We have a few rolling in now as those come in. One question that came in the side here, Tim, as you were presenting, I think that last example, you had just 3 of the parameters in the model. So the SC50 and the 2 S max parameters. How do you constrain a model when there's only a few of the total parameters that you're most interested in optimizing? And another example may be, for example, if you're dealing with a PopPK model and you're most interested in clearance and not so much the intercompartmental clearance. Are there ways of constraining that within PopED?
Yes, there are. And so I mentioned, so we can ignore unimportant parameters. One of the options that actually is available in PopED is the DS Optimality Criterion. So the S, I think, stands for subset, so it allows you to focus on just a subset of those parameters. So you could specify that you're only interested in those particular parameters, and it would optimize the design just in terms of estimation of those.
Okay, great. Another question that came in. So we've looked at cases where we have a fixed number of samples and we're optimizing the actual sampling time. Mm-hmm. Are there ways within PopED to control the optimal number of samples?
Oh, I'm not familiar enough with PopED. Like I said, there's so many options in there that I don't want to say that you can't do it, but not that I'm aware of. What I've done in the past is just, if you know you're going to have between 4 and 6 samples, I would do 3 separate optimizations and see. I mean, obviously 6 samples is going to give you a better estimate, but see whether 4 or 5 samples would be good enough. So yeah, I would do 3 optimizations in parallel, but I don't know if there's a smarter way of doing that in PopED or something else. Okay.
And then also the relative standard error that you get out of the optimality routine. Can you maybe make some mention of differentiating that as being a bias measurement as opposed to precision, and maybe some of the potential advantages through the additional SSE step of getting both the estimate of bias and precision?
Again, I don't want to say that there's no way of doing that, but there's none that I know of, as far as I know. But someone please correct me if I'm wrong on that. All I've done before is just hope for the best, really. But I don't know if there's a better way of addressing that.
Okay. Yeah, my work in this area is long ago is that from that Fisher information matrix, you just get the one measure, and so yeah. that one of the added advantages of doing the simulation estimation is that you don't have to search everywhere in parameter space using that less efficient mechanism, but that then will get you both the precision and bias estimates.
Right, that's right.
Okay, I'm just reading through. As I read, there are a bunch of questions here. I apologize. There's probably won't be able to get to all of these. We can follow up, or please follow up with us afterwards for any additional questions. Kyle, while I read through these and try to pull out some common ones that I can combine together, could you maybe just give a quick introduction to folks as to where they can find other learning materials for the mrgsolve package? I know that there's a bunch that are freely out there.
Yeah, so Tim, if you go back, can you go back to your links page? So like the page here that Tim has linked for mrgsolve, that's sort of like the landing page that we made that just sort of has a bunch of information, and it's sort of like the portal for getting to a bunch of different types of content. So we've got content in different places just because the content's different, but we try to get it all kind of funneled down into this single location. So there's a user guide. You can see our package documentation. I put the package vignettes up there, and then there's on that learn Tim link way up at the top. This is where we put some of the courses that we've taught and tutorials and that kind of thing. Some of them have YouTube videos associated with them, or just it's a GitHub repo that has the contents in there. So, but I would just start going here if you wanted to learn in there. And yeah, this would be and we'll get the materials that Tim's presenting here, and we'll link out to that too from the site here.
Okay, thanks, Kyle. There are a few questions. Again, I'm trying to triage the many questions here as to being able to use either different optimization tools with mrgsolve or PopED with different simulation tools. So Tim had mentioned that it is possible to interface PopED with a number of different simulation type tools, RxODE and mrgsolve. You know, we're most familiar here with mrgsolve, and so we've used that as an example. Other questions asking if we can use PFIM, for example, or non-mem in one case with some of these things. So my understanding is non-mem really will be useful for the simulation estimation side of things. PFIM, we have used that with mrgsolve in the past. Haven't used that in a while. The support, and Tim, maybe you can add a little bit to this, but the support for PopED has been a bit more consistent as of late, and so we've been more apt to go that route over PFIM, but it has worked for us in the past. It's just been a little while since we've used that.
Yeah, I would agree with that. But yeah, PopED is getting a lot of attention. It's being actively developed. There's a lot of new features and coming out, and bugs fixed and everything. So PFIM, yeah, I've used that quite a bit in the past as well. Not necessarily with mrgsolve, but I just find that PopED, I'm hesitant to recommend one over the other. It's been a while since I've used PFIM as well, but PopED just seems to meet my needs for what I need at the moment.
Okay, just quickly here in the last minute, and again, I'm sorry, we're not going to be able to get to all of the questions here. A question as to a publication demonstrating the actual performance, maybe like a prospective evaluation of how the designs did.
Oh, okay, performance in terms of actual.
Yeah, we ran the optimization. How well did it in fact work out?
There are papers on that have published results from prospectively optimized studies. I can include some links. I'll update these slides and include some.
Okay, great. Yeah. Okay. Well, thank you, Tim, and Kyle for jumping in as well here. So I hope everybody enjoyed this. Feedback is welcomed. We will be sharing the slides, a link to the slides through email as a follow-up within the next week or so here. And a recording will also be available of the session if you have any colleagues that may not have been able to join us here today or want to re-listen to some things to catch things through a second or third time, please feel free to do that. Again, the postings for all that will happen within the next about week's time. And look for further cooped ups in the future. If there are topics that you'd like to hear as a topic area for that, we'd love to hear that as well. Thank you all for attending today. Take care.